So this is Math317 Operations Research Lecture 2. I have stored some stuff on the sideboard that we'll get to later today when we talk about how to do linear algebra a little bit more efficiently than you've probably seen. And again, one of the main themes of the course is the difference between theoretical mathematics and mathematics that you can actually use. A lot of times we have these wonderful algorithms which in principle can do what you want, but the runtimes are so tremendously large that they're not practically useful. And so what I really want to do is I want to emphasize how you can often, with a small tweak, do things tremendously faster. And so I thought I would start off with one of the earliest successes of mathematics, Babylonian mathematics. Okay, how many people understand and remember Babylonian mathematics who've not been in a class with me and heard this speech? Okay. What did the Babylonians love for their mathematics?
Wait, sorry, were the Babylonians the base 60?
Yes, they were the base 60.
Okay.
Why the hell would you use base 60? We have 10 fingers.
I think.
Yes.
So it was because they had to merge a base 5 system and a base 12 system. The base 5 was one for each finger on the right hand, and the base 12 was one for each digit on every finger except your thumb.
Okay, that's more than I knew, so thank you.
Okay.
So we're doing base 5 and base 12. Yeah. What I always heard is that 60 factors beautifully in many different ways. That you can, it's divisible by 1, not surprisingly, 2, 3, 4, 5, 6. We don't do 7, don't do 8, 9, no, 10, 12, lots of different ways to divide it. So when you don't have a decimal system, when you want to break things up, working with 60 is really nice. How many of you remember your 10 by 10s table? This is essentially, are you awake right now? Okay? If you do not know your 10 by 10s table, we have issues here. Right. Some schools make you go up to 11, so that's not so bad. Some schools do 12. I don't think anybody really does 13. Because of our positional system, if you can multiply one-digit numbers, lather, rinse, repeat, the shampoo method, you can just multiply large numbers by doing it in smaller bits and then carry. How many multiplications naively do you need to learn to do base 10 mathematics? How many things do you have to memorize? 50. Okay, so you're giving me the smart answer. The not a smart answer would be 100. And then you would say, oh, wait, we have commutativity. That x times y is y times x. So how many ways can we do things? Well, we have to be careful about repeats. So we have 10 choices for the first number, times 9 choices for the second that are different. And then we have to divide by 2 because we don't care about order. Another way of looking at this is just 10 choose 2, the number of ways to choose 2 numbers from 10 when order doesn't matter. Then we have to have the repeats. And how many repeats are there? These are the squares. So there would be 10 of them. So it would be 10 choose 2 plus 10 choose 1, which is approximately 1/2 of 100. So it's a 50% savings. This is not a tremendously difficult task to ask people to do. If you look at the average person in the world, even the average person in the world can do this. Right. Imagine, however, that you are a Babylonian. So if you want to do your 60s table, 1/2 60 times 60 is approximately 1800. Do you want to memorize almost 2,000 multiplications? I was waiting to see if anybody really wanted to do that, and then you could report back to us later. And he'll ask you, what's 37 times? Okay, so nobody wants to do this. So the Babylonians had a clever idea. It's the idea of a lookup table. And this is one of the greatest advances we have. It allows you to pre-compute things and then use the value of those computations later. So you have a one-time cost. For a lot of things, it could be very expensive to do it the very first time. But that's okay. You only need to do it once and then you save it. I was actually just telling a student last night that when I was a college student writing a thesis on number theory, Riemann zeta function and zeros and primes, I needed to compute huge tables of primes and huge lists of zeros. And they allowed me, I worked in the library, microfilm, microfiche. If anybody has seen those, I'd be amazed. to use the library computers in the microfilm, microfiche office on the weekend, so long as they were done by 9 a.m. And it was a slow calculation. It took a couple of weeks to do it, but I only had to do the calculation once. There were other things I could do while I was doing it. There wasn't that much of a need to optimize the code. If you only need something once, you can afford to be inefficient. If you're going to be using it again and again and again, let's say you have a cell phone that's going to be trying to connect to things. You want to have that connection as efficient as possible. If you want to transmit information, you want to transmit the information as efficiently as possible. So for the Babylonians, they could compute these values once, and they could store them on clay tablets. What's the problem with this?
Clay tablets are heavy.
Clay tablets are heavy. Well, there's a totem pole, there's a hierarchy, and you can have the low people lugging around the clay. Well, even if you have people lugging along the clay tablets for you, it's a pain to use that many. And it's a pain to carry that many around, and it's a cost to make that many. So what the Babylonians did is they had a clever way of multiplying numbers. So to multiply x and y, they did x plus y squared, subtracted off x minus y squared, and divided by 4. So your first instinct should be this is one of the stupidest things you've ever seen in your life. Rather than multiplying two numbers, I'm going to do one addition, two subtractions, two squares, and then another division. This is actually better. Why is this better? Yes?
I mean, the addition and subtraction are pretty easy. You only have
Good. So first, I'm going to pause you first. So first, addition and subtraction are easy. So their cost is almost nothing. And second,
you only have to store the squares.
we only have to store the squares. So the number of squares we need to store, maybe it's around 60 or maybe 120 because we have to go a little bit higher. That's not so bad. Division by 4, not so bad. So the key insight here is that something that you may have done one way all your life may not be the best way to do it. And if any of you have anybody take advanced analysis classes and seen something like this? This does occur in some advanced number theory classes, some advanced analysis classes, in terms of ways to look at things and ways to decompose things. It's a wonderful idea. But the principle is that you can decompose things. Now, if I gave you 37 times 42, let's do 34. We could figure this out because we would have this on our table. What if I gave you 34.2 times 42.6? How might you do this? So it's no longer on our table. Do you have any rough idea of bounds for this?
I mean, it'll be between 34 times 42 and 35 times 42.
Good, so we could take the smaller, and then we get a lower bound. We could take the larger and get an upper bound. And then the idea is maybe we could have some kind of interpolation that takes two values like this and looks at the values that are near them and figures out how to do it. The simplest thing is we could say, well, let's take a number that's maybe look at some way, this is maybe like 2/10 of the way. And first maybe multiply 34.2 by maybe 42. There's a lot of things you could try to do to fill in the gaps. And I'll let you try to think about that. I think you have a homework problem or two where you're asked to try to figure out how might you interpret something like this. How might you try to interpolate from known values to other values? If you look at a lot of tables, you must be looking at an old book, because almost no books now have tables. When I was young, you would have tables of trig functions. You would have tables of log functions. And you would use these to figure out values, and then almost certainly you wouldn't have exactly the number you wanted, but you would have ways to interpolate between. If you know some calculus, you can actually use that to try to estimate how much you would shift things by these increments. And you could write this as like 34 plus delta x, where delta x is 0.2, and maybe 42 plus delta y, where delta y is 0.6, and figure out how things would change. And you would have a delta x term, a delta y term, and a delta x delta y term. The delta x delta y term almost surely is insignificant. And so you could play games like that. Okay, so this is the Babylonian mathematics. And so we talked a little bit about Horner's algorithm last time. And we've talked about trying to do things efficiently. We're going to see how well the camera moves. It's not moving too badly. Okay, so when we did Horner, this was for fast polynomial evaluation. And it was much better than brute force. So brute force, if we had degree d, it took 1 plus d steps. And now, how many of you have seen that this is equal to d plus 1 over 2 by induction at some class in your life? If you have a good calculus class, you should actually see it there as a way to test the fundamental theorem of calculus, that the area under the curve is given by the antiderivative at b minus the antiderivative at a. And you want to test the fundamental theorem of calculus. Well, if I give you the function sine of x and ask you to test the fundamental theorem of calculus, you need to be able to compute the area under sine of x. That's a tough curve to find the area under. What's the simplest curve to find the area under? F of x equals?
Any constant.
Any constant. So let's take f of x equals 33. We can find the area under that very easily. It's going to just be a rectangle, not a big problem, and we can show that this agrees with the fundamental theorem of calculus. This gives you a little confidence that the fundamental theorem of calculus is correct, but not a tremendous amount because the areas of rectangles are not that bad. What's the next simplest curve we could look at? After a rectangle?
Triangle.
Triangle. So we could do y equals ax, or f of x equals ax. And if we do that, that's where you're going to get a sum like that arising. And then you can see that the fundamental theorem of calculus gives the right answer for a triangle. If you then wanted to do a more interesting thing, if you wanted to do a quadratic, then you would have sums of squares. And then that would be the first non-trivial test of the fundamental theorem of calculus. Because now you're showing that the area under a parabola agrees with what the fundamental theorem predicts. That's more convincing to me than areas of triangles and rectangles. Okay, so you've seen numerous times that this is equal to d plus 1 over 2, which means that if d is large, it's essentially 1/2 d squared. What I want to do is I want to talk about how could you estimate. So let's say f of d is 1 plus 2 plus d. And I want to estimate how large this is as d grows. So I want upper bounds and lower bounds. And what you should do is you should start off with the simplest, trivial, easiest thing possible. You can be a smartass here. Can somebody give me a lower bound?
0.
Yes. You could be a little bit better than 0, but...
D.
No. Okay. Well, no, d's too much better. 1. So clearly 1 is less than or equal to f of d, right? I'm just using the smallest of the terms. Then I could say, well, actually, I could do a little bit better. D. All right. Can somebody give me an upper bound? Yes.
D squared.
Good. I was hoping nobody would say positive infinity. And you get d squared by saying, look, we have d terms. Each term is at most d. So the question is, have we done enough that we can stop and say we understand the size of f of d, or do we have more work to do? What do you think? Is this good? Can we rest on our laurels, or is there too much of a gap between the lower and the upper bound?
Does that depend on what you need it for?
I'm sorry?
Why would it depend on what you need it for, I guess?
Right, but I want to have a sense of the size of f of d. And so do you think that the upper and the lower bounds are sufficiently close? Yeah.
I would say no, because they have different growth rates.
Yeah, they have different growth rates. This is growing linearly, this is growing quadratically. What's the true growth rate of f of d? So I need a better bound. So there's a lot of great ways to try to estimate this. And again, I understand for this problem that this is in some sense overkill. We actually know the value is 1/2 d plus 1. I'm choosing this because we know the answer, so that we have something where we understand what's going on, and I want to explain the method of how to attack something like this. This is not a problem where we need to do this, but there were other problems where it will be very useful. So the question is, can we get a better lower bound? And so what we did is we looked at just one term. Rather than looking at one term, we could look at many terms. We could look at, in fact, say d over 2 terms. Look at the last d over 2 terms. Last d over let's write it well, d over 2 terms, all at least d over 2. Right? So if we look at just the last d over 2 terms, we would get d over 2 times d over 2 is less than or equal to f of d, and that's going to be less than or equal to d squared. And so now all of a sudden we have the correct growth rate. We know that it's growing on the order of d squared. We don't know what the constant is. Is it 1/4? Is it 1? As an interesting aside, if you add, yes?
How did we know the second to last line?
Well, if you have d, if you take just the last d terms, you have d, d minus 1, d minus 2, going all the way to d halves. Each of those terms is at least d halves. So I'm just looking at the middle and everything above the middle. So what's the average of 1 and 1/4? Two constants. What's the average of 1 and 1/4? I'm sorry?
5, 8.
Nope. I get 1/2. There's more than one way to take an average. Most often when you do an average, you do the arithmetic mean. You add the two numbers and divide by 2. There's other types of averaging you can do. You can do the geometric mean. And again, one of the whole points of this class is the importance of choosing the right metric for a problem. So this is worth talking about in terms of trying to come up with generalizations of concepts. How do you extend things? We've done the absolute value, since we were little kids. The absolute value of 5 is 5, the absolute value of -5 is 5. We can talk about the absolute value of a vector. What do we mean about when we say the absolute value of a vector? We mean its magnitude. So sometimes people might write 2 vertical lines to indicate that this is the length of the vector. And other times people will just write like this. How many people have seen books that really use this? How many people more often see something like this, where they overload and they generalize the notation? And this is a good extension of the absolute value to more objects. We want properties of the mean. Properties of a mean. So let's assume 0 is less than x, is less than or equal to y, is less than infinity. What do you want? Give me a property you want about the mean of x, y. Yes?
It's greater than or equal to x and less than or equal to y.
Good, so it should live in the interval x, y. Right? If I take the average of two numbers, the average of 1 and 7 should not be 23. Okay? What else do you want to be true? Any special cases?
If x equals y.
Beautiful.
Mean
Is
x.
yes. I really want these properties to hold. If these do not hold, it should not be considered a mean. So I can't remember if I said this in the first class. Whenever you speak up in class and make a good comment, please email me so I can put it in the grade book so that when I have to write letters of recommendation, I can say non-trivial things. If you make a bad comment, I will forget about it. I'm always short on sleep. My kids keep me up to all hours. They get up early now. But also, the reason I want you to do this is I want you to get used to speaking up and getting noticed. The more comfortable you are speaking up here, the more this will propagate to other parts. So I want both of these properties to hold. And it turns out x plus y over 2 and x times y square root both work. They will both satisfy these two properties. So these are two different notions of a mean. It turns out that there's a lot of other notions of mean that you can have, and that there are relations between the means. There's relations between, this is called the arithmetic mean, and this one is called the geometric. And for a lot of things, the geometric mean is actually better. And if we take the geometric mean of our two constants, 1/4 and 1, the geometric mean of that is 1/2. Okay? Now, if you want, you can start asking other properties of the mean that you might want to have. What if I take the mean of two means? How should that be related to the mean of just the four objects? And so as an exercise, to think about, how could you try to generalize this? What other properties would you like? How many people have taken a statistics class? Okay, I've only taken them from the psychology department, but I am still allowed to raise my hand. Have you seen the method of least squares, one of my favorite methods in all of mathematics? Why do we measure error in the method of least squares by squaring things and not absolute values, or even better, unsigned errors?
We can use calculus.
We can use calculus if we square. The absolute value function is not differentiable. So every now and then I will say something that might only apply to a subset of people based on the classes you've taken. You do not need statistics for this class, but just in case you've seen it, we like to use squares for errors because calculus is available. It's not available for the absolute value function. There is a real choice of metric. Yes?
Is it worth using the square?
So the way I phrase it is, if I'm hired to do the analysis, I use squares. If I'm hiring someone to do the analysis, I have them use the absolute value. I think the absolute value does better for many things than squares. One bad observation has a tremendous impact with squaring. It doesn't have that same impact with absolute values.
Why do they only teach us squaring? Is it easier?
Because squaring has a closed form expression using linear algebra. And you can just write down the answer for the best fit line using the method of least squares. You can't do that using absolute values. Also, we have to justify all those calculus classes you took. Right? I mean, when you take calculus, do you have any idea at first why you're taking calculus? What this is good for? Only once in my life has someone come up to me on the street and asked me for an area. And this was near Berkeley, California, where you have some strange people. But calculus gives you probabilities of events. Areas under curves can be interpreted as probabilities. That's useful. Okay, so we have some idea of how to estimate the size of simple things. As an application, we're not going to do really anything on this, is n factorial is n times n minus 1 all the way down to 3 times 2 times 1. And you can play the same game we just did, using the sum of 1 to d to try to estimate how large is n factorial. To try to get upper and lower bounds, try to get a sense of what is the true order of magnitude. This idea of dyadic decomposition, of breaking things in half, analyzing each of those pieces, and then feeding it together, that's a great application. The key result here is Stirling's formula, which says n factorial is about n to the n, e to the minus n, square root of 2 pi n, and then it's 1 plus an error of size 1 over n, and then a smaller series in terms of higher and higher powers of n. But you can get some quick estimates to this using the idea we did a moment ago. All right, so the Babylonians were great. They gave us the idea of a lookup table, or if they didn't give it to us, they at least used the idea of a lookup table. All right, what I want to do now is I want to turn to the numbers on the board. So over here, I have hopefully not copied anything incorrectly. Here are 7 numbers involving A's and B's with 2 subscripts each, and then I have C equals AB equals the following. Any guess what this is trying to do?
It saves a multiplication on the matrix.
Yes, the idea is to save a multiplication when we multiply 2 matrices. So in the beginning, we will assume that all matrices are 2 by 2. And we will understand 2 by 2 matrices in complete detail. And then we will try to build up to larger matrices. It would be wonderful if the only integers in the world were powers of 2, or at least the only sizes of matrices. Because then we could build it up as blocks of 2 by 2 matrices without any misfittings. You frequently have this power. Not to convert all integers to powers of 2, but to choose to sample things at a power of 2. If you want to sample things 1,000 times or 1,024 times, 1024 times is often a little bit easier to code because things are then coming in with powers of 2. Okay? So this is an implementation issue. Theoretically, it doesn't matter, but when you're writing the code to actually implement things, it's nice if things are power of 2, things fit together nicely, and you don't have to worry about those pesky remaining cases. All right, so linear algebra is a prereq for this course. One of the things I am assuming you are familiar with is how to do the standard way of multiplying matrices. So if I give you two matrices, A and B, they give you a new matrix C, and the way it works is as follows. Here is row AI. Here is column BJ. And then when I do the dot product, I get Cij. Okay? How many of you have seen a motivation for why we choose this as the definition of matrix multiplication? And how many of you is this somewhat similar to Moses coming down from Mount Sinai with commandments from God as to how we shall multiply matrices? Thou shalt take the ith row of the first matrix, and thou shalt dot it with the jth column, and thou shalt see it is good, and thou shalt call it Cij. How many of you have not seen a motivation as to why we do this? Okay. I will not say anything with the cameras rolling about your linear algebra classes, but you want to have an understanding of why are we defining things like this. We can define almost anything we want in mathematics. Most of the definitions will be useless. What we want to do is a matrix is a transformation. So this is the big idea. A matrix is a transformation. How many people speak more than one language fluently? More than one language somewhat. I won't count programming languages for this. You should hopefully, if you speak multiple languages, you should hopefully be able to pass from one language to another. Now, it becomes a very interesting statement, or a very interesting discussion as to, can you discuss certain ideas in certain languages? Or if you don't have certain words for certain concepts, how does it impact? Can you understand certain writings if you're not reading them in the native language? If you've read 1984 with Newspeak, there's a lot of wonderful discussions about stuff like this. Linear algebra is to some extent a translation from one basis to another. The idea of linear algebra is to choose a basis that is convenient for what you want to do. So we're going to hold off on matrix multiplication for a little bit and go back to something that you have almost surely forgotten from high school or junior high, conic sections. Okay, I can't help but smile. They're so wonderful, right? If I give you an ellipse aligned with the coordinate axes, and this is A and this is B, then we have x over A squared plus y over B squared equals 1. There's a beautiful theory about hyperbolas and parabolas and lines and slicing two cones and getting all this stuff. We're not going to get into that. How many people have not seen an ellipse like this? One of my favorite comments about ellipses is when Kepler was working out his laws of planetary motion, he was analyzing Mars, which was a great planet to analyze. And at one point he wrote down the equation of motion for Mars, and he goes, if only it was an ellipse. And it was an ellipse. But it was written down not in the standard form of the ellipse. He didn't recognize that he had written down the equation of an ellipse. There's a tremendous value in terms of knowing how to look at things the right way. If time permits at the end of class, I will give an example of how to look at things the right way. What if I give you an ellipse like this, where it's no longer aligned with the coordinate axes? Does anybody remember from high school how to solve this? Anybody remember from linear algebra how to solve this?
You need to rotate it onto
Yeah, you basically just go like this, right? If you draw your coordinate axes like this, u and v, we can write down the equation in uv space very easily. So what we do is here are the xy axes. So we have a rotation matrix R that sends xy to uv. And then we know what the equation is in uv space. In uv space it would be uv 1 over a squared, 0, 0, 1 over b squared, uv equals 1. And now if I want to get into xy space, well, if r times xy is uv, then xy is r inverse times uv. And since it's a rotation matrix, the inverse is actually the transpose. So we would then get xy r transpose 1 over a squared, 0, 0, 1 over b squared, r xy equals 1. And here is how to get the equation of an ellipse when it's not aligned with the coordinate axis. This is in some sense what linear algebra is all about. It's finding the right basis for the problem you're studying. Depending on what you're looking at, one basis is more convenient than another. In case it's not clear by now, I love Boston. I love the Boston teams. I hate New York City. I hate most of the New York teams. You Mets are okay. But I have to tip my hat that there is part of New York that does something better than Boston.
Coordinate system.
The coordinate system in Manhattan. Okay? The coordinate system in Manhattan is very logical. Unlike Boston, where you can have Beacon and Commonwealth flip as to which one is on top. Now, if you are walking in Manhattan, which looks like this, how should you orient your coordinate system? This is screaming at you how to choose your axes, right? The north, south, the east, west, like that. Okay. It doesn't matter if it's not exactly north, south, and not exactly east, west. You have a nice rectangular grid. That's how you want to view things. Okay. When we are doing linear algebra, we have a matrix is a map from a vector space back to a vector space. And so if I have A, B acting on a vector V, I want this to be the same as A acting on the vector BV. And so I want some matrix C that's going to be the same as B followed by A. And that's where the definition of matrix multiplication comes from. I want to choose a matrix C such that the effect of C is the same as first applying B and then applying A. And when you do that, it then forces this what looks initially as a strange row, column, dot product. That's where it comes from. So it comes from writing down transformations. If you want to use matrices, you have to choose a coordinate system to use matrices. Depending on your coordinate system, the transformation will look very differently. In linear algebra, you might have heard about the principal axis theorem. If you have a real symmetric matrix, it has a basis of eigenvectors, and you can write it down as a diagonal matrix with the eigenvalues. That's telling you this is a good basis to use for this matrix. Because then all it's going to do is just rescale things in those directions. Okay, so this is the explanation of how we multiply matrices. Let's go back now to the statement over here. This is a claim that this is going to be equivalent to A times B. Now, if you look at this, this is a lot more complicated at first inspection than just doing straightforward matrix multiplication. If I give you 2 by 2 matrices, A11, A12, A21, A22, B11, B12, B21, B22. If I multiply them, well, the first element is going to be A11, B11, plus A12, B21, blah, blah, blah. Those aren't that bad. So the question is this worthwhile? Well, the key fact, as was noted, is there's only 7 multiplications here. How many multiplications does it take to make each coordinate here? It takes 8 multiplications. So this costs 8 multiplications. This costs 7 multiplications. Now, if you want to look at additions, this has 4 additions. What about over here? Okay, so I've got 7 multiplications, 2 additions, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I think it's 18 additions. So is it a good deal to trade 1 multiplication for 18 additions? Yes, especially when you have big numbers. And so this is an extremely valuable trade to make. And so the question is, how expensive is it to multiply matrices? Well, I will assume that n is a power of 2 just to make things simple. Let's say A and B are n by n. So the number of brute force multiplications for C equals AB is what? So if I wanted to multiply two n by n matrices, how many multiplications would that be? It would be n cubed. It's n multiplications to get each entry. I have n squared entries. Using, this is called the Strassen algorithm. It's n to the log 2 base 7. The way you should really view 3, how should I view 3? Log base 2 of 8. And by saving one multiplication, when you expand things upwards, you change the exponent from the log of 8 base 2 to the log of 7 base 2. So the log of 7 base 2 is approximately 2.807. And amazingly, this is worth being excited about. Lowering this exponent a small amount has tremendous applications, because you have to view n as large, 10,000 by 10,000, 100,000 by 100,000 size matrices. And then any exponent savings is going to have a phenomenal impact in runtime. And so it's going to change what you're able to investigate in a reasonable amount of time. So, again, I'm trying to balance the theory and the applications in a class like this. Theoretically, is there any need for something like the Strassen algorithm? No. You could just multiply matrices. But if you actually want to do things in the real world, this will change what you're able to do. And if you're doing simulations, it could change how large you can simulate. So it is tremendously valuable to be able to do something like this. Okay. Any questions on this? What would happen if n was not a perfect power of 2? If n is 4, I could have it as 2 by 2 blocks in here, right? So if n is 4, I can handle it without any trouble. But what if n is 5? What would I do?
Use the binary expansion, so you have 4 of these and then just ones.
So what size matrix should I look at if I have 5? Yeah, I could look at 8. And I could put, 1, 1, 1, 1 down here, and big zeros everywhere else. And just add blocks of zeros and ones. And if I do that, then I can actually run it. And I would just have to take the smallest power of 2 that's as large or larger than my matrix size. So you can pad the matrices, yes?
So why would we do that if we're doing that for 5? Why don't we just try to compute for 5 instead of just trying to change it and add 1?
So one question is, which is going to be better? For 5 by 5, doing it directly or doing it something like this? For 5 by 5, it might actually be better to do it directly. The question is the savings going to be sufficient? Because you're going to have to do a few more things because now you've made it larger. But as you go higher and higher up, there will be a critical transition point. And then this becomes a nice exercise. At what point is it worth transitioning to the Strassen algorithm rather than doing things by brute force? In my thesis, I don't want to go into all the technical details. I was looking at ranks of families of elliptic curves and orders of vanishing, and I was getting better results than had been done before, but only if the rank was sufficiently high or higher. So my initial results was, if you want a bound order vanishing of at least 2, it's at most 250% of the elements. You really don't need to do too much of a calculation to show that at most 250% of the time something happens. As you go higher and higher up, once you get to vanishing to order 5 or higher, then my bound is better than what had been done before. But the early bounds were actually worse. It's not that much of an achievement to show that at most 250% of the time something happens. You can usually do that far more elementarily than what I was doing. So it's a really good question to think about, when do things kick in? What I will end with today is just an encouragement for you to find some system that you can program in. You want to try to actually implement these things and see, what is it like to implement? How hard is it? For a lot of things, it's actually easier to do some computer simulations and build some intuition as to what's going on than to actually try to solve the problem theoretically. Or if you've done some simulations and you have some sense of what the answer probably is, when you then do your theory, you might be, that seems strange. I was getting around 14%, and when I do theoretical stuff, I get 0.0005%. That seems off. I don't care what system you program in, but it's good to just try to implement these things and try to do some simple problems to see things. Again, one of the issues is, how efficiently do you need to program? It's going to depend on whether or not you need to do something many times or just once. If it's just once, you can be crude and inefficient. I will end with my most favorite crude example. So this is a math number theory problem. Take the digits 1 through 9, use each number once and only once, and form 3 fractions. A over 10b plus c plus d over 10e plus f plus g over 10h plus I. And there is a way to put the numbers 1 through 9 so that you will get this to equal 1. So it's a nice exercise programming this. So I was at the American Institute of Mathematics many years ago, and somebody mentioned this problem. I'm surrounded by some of the top number theorists in the world, and they start proving theorems about where certain digits must be located. What do you think I did? Yeah, I wrote a computer program. Now, you can actually kill and make it a little bit more efficient. How many ways can I put in the numbers? How many things do I have to check? 9 factorial. Now, 9 factorial is 9 times 8 times 7 times 6 factorial. 6 factorial you should know. What's 6 factorial? 720. Right? So this is 9 times 8 times 7 times 720. Well, this is going to be at most 1,000. So this would be at most 720,000. But actually, I know 8 times 7 is 56. So that's much less than 100. So I might guess that this is going to be maybe around 330,000. And again, just you want to have some sense of numbers and their sizes. How bad is 9 factorial? If I had something of the size 52 factorial, shuffling a deck of cards, you run away in fright and horror. You cannot do 52 factorial. 9 factorial for a computer, not a problem. You can do things a little bit better. You can say, well, look, the order of the 3 fractions doesn't matter. So you have some symmetries. And you can actually cut this 330,000 down a bit. But here's the thing. It would take you longer to code the symmetries than it would take to just write the simple program and have it run once. So it's not worth writing the better program. You run it once, very quickly it goes through all the possibilities, and it turns out the answer. So as a nice exercise, try to code this more efficiently, and think, what can you do to cut down on the 330,000 possibilities, and see how much time it takes you to do that. All right, any questions? So remember, if you are a senior math major and you would like to graduate with a math degree, you should come to the Pizza Fest followed by the colloquium. I think our kickoff speaker is on Wednesday. The following week, we will have, I think, no special guests, but I think we will have special guests the week after that.